solve problems. So for the rest of this course, we're mostly going to view ciphers as black boxes. They provide two functions, encrypt and decrypt. Encrypt takes in a message from some message space and produces a ciphertext, and it also takes in a key from some key space. Decrypt is the inverse. It takes in a ciphertext and a message, and if it takes in the same key, it will produce the same message that we got. And our correctness property is that the decryption with the same key of a message encrypted with that key gives us the same message. For the rest of this unit, we're going to assume that we have some function that provides encryption and decryption. AES is a good choice for most applications. And we're going to look at how to use these functions to solve problems. The first thing we're going to look at, though, is how we actually get this key. All of our assumptions about security depend on this key. And we have two key assumptions. The first is that the K is selected randomly and uniformly. This means each key is equally likely to be selected, and there's no predictability about what the key is. The other big assumption about the key is that it can be kept secret. The adversary can't learn the key, but it can be shared between the two endpoints. This is a big challenge. We're not going to look at that yet this unit. We'll get to that later. This is the big problem of key distribution, which we'll talk about starting in Unit 3. Now I want to talk about this first problem, though, that we need to select a random key. So if we're going to generate random keys, we need some understanding of what randomness is. This is a very deep philosophical question, and I'm not much of a philosopher, so let's try a quiz instead. So the question is, which of these sequences is the most random? So here are the sequences. I won't try to read them, but see if you can figure out which one of these is the most random. And I should warn you in advance, this is a bit of a trick question if you haven't already decided that. So the correct answer, other than refusing to answer the question, which would be a very correct way to answer such a question, the correct answer is the third choice. And there's some ways to know which ones are not correct. I'll show you soon how each of these sequences was generated. Well, if you look at the first one, you see there's a sequence of 0, 1, 1, 0, 1, 1 that keeps repeating. Anything with a repeated pattern like that is definitely not random. Now, the caveat is, well, certainly if you generated a long enough random sequence, eventually it would contain this pattern inside. The other one that is probably the trickiest one, that when humans generate random sequences, they look sort of like this. The property that this sequence has is there's never more than 3 repetitions in a row. And when humans are asked to generate random sequences, well, they usually don't have long runs of repetition. But in real random sequences, there are. You can see there's a sequence of 5 zeros here. There's a sequence of 4 ones. There's lots of repetition. In this, there's never more than 2 in a row. So this is not random. The other 2 look potentially random. You'd have to analyze them a little more carefully. This one has more structure. This one is actually random. And let me show you, and I should say this one is actually close to random. And let me show you how each of these was generated. Here's how I generated each of those sequences. So the first sequence was generated by generating a sequence. I'll show you what generate sequence does next. But for each position in the sequence, the procedure that generates the output generates 0 if the position is divisible by 3. Otherwise, it generates 1. And we do that for the length of the sequence, which is defined as 88. Display bits turns a list of bits into a string. All this code will be available linked from the course. So that is what generates the first sequence. And the code for generate sequence is here. It just maps the function onto the range from 0 to n minus 1. So for that length, we're seeing the output of the function at every position. So that's the first one, and clearly non-random. The second one is taking a string, converting it into bits, and displaying those bits. And the string is this great quote from John von Neumann. And what the quote says is that anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. But of course, we do it anyway. So definitely, that's not random. It's generated from a very specific string. If you knew the string and you knew what these procedures do, you could generate that sequence. And the sequence that it generates is the one that was the second choice here. Looks sort of random, depending on how carefully you look at the patterns, but it's definitely not random because it comes from this quote from John von Neumann. The third one is actually designed to be random. So we're using the random choice method, and that's provided in the PyCrypto library that I'm using to generate random numbers. And it claims to generate fairly good cryptographic random numbers. So this third sequence at least is generated in a way that is designed to be random. The fourth one is generated using this procedure called generate fake random, which starts by making random choices, but is designed to trick humans by not having repetitions greater than 2. And I should change my comment. I had originally done it with greater than 3, and that looks to most humans very random. And I know it was a trick question, but I thought it would be a little too tricky with including greater than 3. But this is a good test for humans. And one of the experiments people sometimes do is ask humans to come up with sequence of random numbers that they think are random from their own head. And they come up with sequences that are easily recognizable as non-random because they don't like to have too much repetition. So that question assumes some notion of randomness, but it's a very fuzzy concept to define. What I think is the most useful definition of randomness is the one that Andrei Kolmogorov came up with, which is based on Kolmogorov complexity. And this is an idea that was developed by the Russian Andrei Kolmogorov, as well as by the Argentinian Gregory Chaitlin. The idea is it's a way of measuring the complexity of some sequence, and it's defined as the length of the shortest possible description of that sequence. For this to be well defined, we need to understand more precisely what a description is. One way to do this would be to say it's a Turing machine and decide on some formal way for writing down a Turing machine. But we could use any method of describing algorithms that we want. It could be a Python program. Whatever we select as our description language, Kolmogorov complexity is well defined. And as long as that description language is powerful enough to describe any algorithm, it's a reasonable way to define complexity. And we can use that to define a notion of randomness. Some sequence is random if the shortest way to describe that sequence is the length of the sequence plus some constant. That means as we make the sequence longer, the description gets longer at the same rate. This matches the notion of randomness that we used informally in the quiz, that if there's a short program that can produce the sequence, that means it's not random. It has some structure to it, and the program shows us what that structure is. If there isn't any short program that can describe that sequence, well, that's an indication that the sequence is random, that there's no simpler way to understand that sequence other than to see the whole sequence. So this seems like a useful notion for understanding randomness. We're going to ask a quiz to see if it seems like a useful notion for measuring randomness. So the question is, for a given sequence S, is there a way to compute the Kolmogorov complexity of S? The choices are that we can. That is the length of S plus some constant. So the second choice is, yes, we can. It's impractical to do this, but here's an algorithm for doing it. We can start by initializing n to 1. We can have a loop that keeps going until we find the correct value of n, which is the Kolmogorov complexity of the string S. And we're going to do that by looping through all the programs of length n. This is a big set, but it's finite. So in theory, that would eventually finish. And for each program, we're going to execute that program, see if it produces S as its output. If it does, that's the result that we want. And the third choice is no, it's theoretically impossible. The answer is that it's theoretically impossible to compute this for an arbitrary sequence. The first answer is not correct. If S is truly random, this would be correct. But if S is not truly random, there might be some shorter way to compute it. So this gives the maximum value of the Kolmogorov complexity of a sequence length S. And an example of such a program would just be this Python program. That would be the program print plus S. That would print out the sequence S. Its length would be the length of S plus the 5 characters for the print plus 1 for the space. But that doesn't prove that there isn't a shorter program that can produce S. The trick in the second answer is this part. This assumes that we can execute P to completion. In order to do that, we would need to solve the halting problem. We would need to know that P will either never finish or know how long to wait to keep running P. So we can't actually do this step. This might run forever. This loop may never finish. And so we would never learn the result. So that's why this doesn't work. This is not enough to prove that it's impossible. because maybe there's some other way to do it. And I'm not going to go through how we actually prove that the Kolmogorov complexity is uncomputable, but I'm going to show you a paradox that will give you a little bit of an idea why that is. And the paradox is known as the Berry paradox. What the paradox asks is, what is the smallest natural number? And by that I mean the set of numbers 1, 2, 3. Sometimes people design it starting from 0. Paradox would work just as well either way. That cannot be described in 11 words. So this seems like a reasonable question. We can define the set of numbers that cannot be described in 11 words. Seems like a perfectly reasonable description of a set. It's also a case that any set of natural numbers has a smallest element. The numbers are well ordered, so whatever that set is, there must be some smallest number. So that means there should be an answer to this question, that there is a smallest number that cannot be described in 11 words. And I'm going to describe it for you. Here's my description, and my description has 1, 2, 3, 10, 11 words. So I just described the smallest natural number that cannot be described in 11 words, but I've described it in 11 words. So that suggests that no such number exists, but that contradicts the properties we had before. And that's why this is a paradox. This is certainly not a proof that the Kolmogorov complexity is undecidable, but it should give you some sense of how we might prove that. So Kolmogorov complexity gives us an interesting way to think about randomness. It's certainly a useful notion in many areas of computer science, but it's not going to give us a practical way to tell if a sequence is random. It won't even give us a theoretical way to do that because it's uncomputable. The next thing we might think about trying is statistical tests, and this is in fact often used as part of an argument that something produces random numbers, and it should be part of that argument, but it can never be the whole argument. That the only thing we can do with a statistical test is show that something is non-random. We can't ever prove that it is random. We could always find some non-random sequence that satisfies all of our statistical tests. So we're left with our best argument is how the sequence is actually generated. If we know how the sequence is produced, we can have some confidence that it satisfies the randomness requirements we have, at least for generating a good key. And the real requirement there is unpredictability, that we want to know if our sequence is a sequence of numbers like this, where each xi is from the range 0 to 2 to the n minus 1, that even an attacker who's seen the first m numbers in the sequence can only guess the next one with the same probability they would have if they were just guessing by chance. Only 1 out of 2 to the n, the size of the elements in the sequence. So that's the property we want. If we're going to get that property, and we can't do it by using Kolmogorov complexity, because that's uncomputable, we can't do it with statistical tests, because they can only show non-randomness, the way we're going to try to achieve that is by generating the sequence in a way that produces values that are unpredictable to the attacker. And quantum mechanics provides a notion of random events, that there are events in the universe that are inherently random, and we could count things like radioactive decay with a Geiger counter and use that to generate randomness from physical events. Thermal noise is an easier thing to measure in most circumstances. If you can measure that precisely enough, it also depends on quantum mechanics at some level and produces a randomness. And many modern processors have ways of generating a small amount of randomness by measuring thermal noise in the processor. Whether it's really physically random depends on a lot of other things. You can also look at things that actually happen and think that they're random. Maybe if they're key presses or user actions, maybe those are random. An example of this is when we generate a new key using GPG. It will ask you to generate, when you start to generate a key, it says we need lots of random bytes. And you can perform some type of action like moving the mouse using the disk to help generate more randomness for it. And humans aren't good at doing random stuff. When we move the mouse, we're probably moving it in a pattern. When we type on the keyboard, maybe we're doing things that are not very random. So unless you're generating your randomness from quantum physics, there's always some question whether it's really random enough or whether you could predict the particular motions I took. And certainly, given that this has been recorded and released, the fake key that I generated for Alyssa B. Hacker should not be used for any secure purpose. So this approach of waiting for physically random events is okay for GPG maybe, because someone using it is probably patient enough to be willing to sit around for a while doing random stuff as well as a human can to generate a key. This would not work very well when you need more randomness more quickly. And this happens every time you do a web transaction. Every time someone does a secure web session, anytime you see the lock key in your browser, there's a protocol going on called TLS. We'll talk about that more in a later unit. But one thing that requires is a new random key for each secure web session. I don't think many people would tolerate being asked to move around their mouse and do strange things to generate enough randomness in the hopes that that key is secure every time you connect to a website. So we need something better. We need a way to take a little bit of physical randomness, and that's usually known as the seed. That's the initial state, and that's the input to what's known as a pseudo-random number generator. And that produces a long sequence, this longer than the amount of physical randomness we started with, of random bits. So that's our goal, to take a small amount of physical randomness, some source of entropy that we can use as a seed, have some function that will compute from that seed a long sequence of apparently random bits. So for this quiz, I want to see if you can figure out a sensible way to do this. So we've got some pool of randomness, and one approach would be to extract a seed from that pool, use our encryption function. We'll make the seed the message. We'll select the key as 0. We'll get an output from that, and we'll make a copy of the output. That's going to be our first random value. Then we'll encrypt again, using the previous output as the new input, using the key 0 again, and extracting the next random number. So the second option, we're going to extract a seed from our random pool. We'll use that as the key to encrypt. And for the first random output, we'll get the result of encrypting 0 with that key. For the next one, we'll get the result of encrypting 1 with that key. We'll keep using the same key, encrypting and getting a new random value as our output. And for our third option, we'll extract new values from the random pool each time. We'll encrypt a message selected from the random pool with a key selected from the random pool to get x0. To get the next random number, we'll extract a new message from the random pool and a new key and do that encryption. So which one of these options makes the most sense for a pseudo-random number generator? And let's assume our encryption function behaves well. It provides a mapping between keys and messages that's hard to invert if you don't have the key. And that we have a random pool that provides a limited but good source of randomness. The best option is the second one. The problem with the first option is it doesn't provide the unpredictability property that we need. If an attacker knows x0, they can easily compute x1. And that's a property our pseudo-random number generator needs to have. The third option seems reasonable. It requires a lot of randomness in the pool. But if we have that much randomness in the pool to extract a new random value for each random output, well, we should just use that. Right? If we do have enough randomness for this, there's no reason for all these other steps. We should just extract something for the random pool each time. And we're not able to do this. We're assuming we don't have enough randomness to do that. So we're using things that aren't actually random here if we're extracting them from the random pool more quickly than we're actually able to produce new randomness here. It's doing a lot of extra work, but it's eventually starting to use values that are not random as the inputs to our encrypt. And if those values are predictable, well, then the outputs become predictable too. So that doesn't work. So the best solution is this middle one, where we're extracting a seed once, we're reusing that seed, and we're encrypting a sequence of values, which can just be a counter, and each time using the output of that encryption. So this is a good start for a basic design for a pseudo-random number generator. We have some pool of randomness. We extract a seed from that pool. We use that seed as the key to our encryption algorithm. And as the messages, we use a counter. So let's suppose we use AES 128. So that means the key size and the block size are 128 bits. And so each time we do this, we get 128 bits out, which we use as our random values. And this counter will go up to 2 to the 128 minus 1, and then go back to 0. So now I have a quiz about how well this works. So the question is, does this produce a sequence that appears random? And let's say for the first 2 to the 70 outputs. So certainly if we have more than 2 to the 128 outputs, well, these counter values repeat. So that would be non-random. The choices are yes, no, because it repeats values too frequently, or no, because it repeats values too infrequently. The answer is no. It repeats values too infrequently. This may seem a little surprising. If it was random, well, the probability of 2 consecutive values being equal should be 2 to the negative 128. A very low probability, but not 0. If this is an encryption cipher, well, it satisfies the property of invertibility. So any value that's different here encrypts to a different value. So that would mean that for our actual pseudo-random number generator, this probability is actually equal to 0. And that's different from what it would be in a real random sequence. This probability is low enough that we still wouldn't expect a repetition for a long time, but we would expect to have one within the first 2 to the 70 outputs. And we'll talk soon about the birthday paradox to see why we would expect one this soon. Still a pretty big number, but it would be enough to distinguish this from pure randomness. So to fix that, there's a couple things we could do. One is to occasionally change the key. And after some number of outputs, we can take one output. Instead of using it as an output, we use it as the new key. So even if we don't have any more randomness, we'll still change the key. That will affect this probability. It will no longer be 0. We'll start seeing values that have some probability of repeating what we saw with the previous key. So we'll get a new key every few million outputs. The other concern is whether this pool of randomness is good enough. On Unix machines, there is a pool of randomness stored in dev random, and it's collecting events that are believed to be random and out of the control of the attacker. These could be user actions like key presses. These could be things that you collect over the network. There's some risk that these could be compromised, that some of them could be controlled or at least predictable to the attacker. So we want to have multiple pools of randomness and combine them in a way that makes it very difficult for an attacker to control this seed. And this is essentially what the Fortuna pseudo-random number generator does, and that's one of the more popular, widely used ones. It does use this rekeying to avoid this apparently non-random property. And it uses multiple pools of randomness selected in a way that makes it very hard for an attacker to control what the seed is, even if the attacker can control one or a few of the pools of randomness. So the key point is if you're generating keys, it's really important to use good randomness. Generate keys in a way that makes them unpredictable. And there was a study recently that looked at public keys. We'll talk about asymmetric crypto in a future unit. But the problem in generating those keys was not using good randomness. And this was widely reported in the press, often a somewhat misleading way, talking about the encryption system being broken, which it wasn't. All that was broken was if you pick bad keys, the encryption doesn't work well. So you should be careful not to use the built-in random generator in your programming language. It probably is not cryptographically secure. There are good random number generators provided by cryptography libraries, like the PyCrypto library that we'll use for some of the code in this class, that implements the Fortuna random number generator. So now that we have an understanding of symmetric ciphers, and we know how to generate a random key, we're going to talk about an application, which is to store a file securely. And our goal here is that we have, this is the computer. It may look more like a stapler, but it is intended to be a computer. And we have on that computer, we have some file. What we'd like to do is store that data on the computer. Know that if we leave the computer in a coffee shop and someone captures the computer, they won't be able to read the contents in that file. This is to prevent the kind of incident one hears about fairly frequently in the news, where someone has a list of social security numbers for everyone at the DMV, at the driver's licensing office, and they leave that on their laptop and it gets stolen. And then you've got a big worry about all that personal information being lost. Probably that kind of file shouldn't be stored on someone's laptop in the first place, but our goal is to be able to store files that contain sensitive information and know that even if the computer that they're stored on is stolen, the contents of the file will still be secure. Now, we don't want to just throw the file away. We want the owner of the file to still be able to read the file. And so we're going to assume that there's some key that the owner of the file can store in some other place that's secure. We'll talk a little bit later how we might want to do that, but let's assume there's a key that can be used to decrypt the file. So here's the straightforward way to do this. We're going to take our file, we'll call it M, and we'll divide it into blocks. And the block size will depend on the cipher we're using. Let's assume we're using a cipher with a 128-bit block size, which is the size that AES uses. Then what we'll store is the ciphertext. And each ciphertext block is the result of encrypting, using the key K, the corresponding message block. So how well does this work? Let's try a quiz. So the question is, assuming that E has perfect secrecy, we know this is not true because we're reusing the key to encrypt multiple messages, and Claude Shannon showed that this would only be possible in the case where the number of possible keys must exceed or be equal to the number of possible messages, and that's not the case here. But let's assume that for now. What can an attacker learn if they capture the laptop and acquire C? Check all the choices that are true. The choices are nothing, the length of M, the value of K, which blocks in M are equal. The answer is the attacker can learn both the length of M and which blocks in the message are equal. The attacker learns the length because the length of the ciphertext is actually equal to the length of M. The output for our encryption function is the same length as its input, so we know that these lengths are equal. This assumed that the file contents M were an even number of blocks, since we're dividing M into blocks. If it's not, we'll have to do something about that, and we'll get to that soon, but the solution to that is to add padding. The other issue, which is a more serious one in this case, is the attacker learns which blocks in M are equal. This might not sound like such a big problem if we're thinking of the blocks as 128 random bits. Maybe the probability that two blocks are equal is actually very low. We'll see later this class it's not quite as low as you might guess. But the message is not random bits, right? The message of the file, if we're thinking of these as 8-bit characters, well, 128 bits is only 16 characters. If they're Unicode characters, well, then we have more than 1 byte per character. This could get down to a pretty small number of characters. There's certainly lots of sequences in many files that would be 16 characters long that could be repeated. So this is a pretty large amount of information to leak. We want to find a way to encrypt our file that doesn't do that. Ways of using ciphers like this are called modes of operation. The one that I just described is known as electronic codebook mode. And the reason for that is you can think of having a book that for each input message, 128 bits of input, there are 2 to the 128 minus 1 inputs, you would be able to look up the value of encrypting that message. So you could have a code book that gives you for each input the 128-bit output that corresponds to that input. And this would be a really big book. If we assume we could get about 10,000 entries on a page, and each page weighs 5 grams, well, this would be about 1.7 times 10 to the 32 kilograms to carry around. And that's just for one key. So it's certainly not practical to think of this as being a physical codebook today, but this is really the same thing that the early codebooks did. They just provided a one-to-one mapping between inputs and keys. And that's exactly how we're using AES here, is to provide that mapping. And we're using the same mapping every time we need to encrypt the same value, we're getting the same output. This is the problem that we mentioned earlier, that it doesn't hide repetition in the message. Another problem it has is that someone could scramble. An attacker could move blocks around, could replace blocks, could change things, and it would still decrypt to a perfectly valid message, just with the blocks in a different order. So those are problems with the electronic codebook mode. We're going to look at some alternatives that avoid some of those problems. One way to avoid some of those problems is to use cipher block chaining. The idea here is that we use the ciphertext from the previous block to impact the next block. So here's what this looks like. So we're still going to break our message into blocks. So this is the idea of cipher block chaining. We're going to take each message block, encrypt it with our encryption function. Let's assume it's still AES, using the same key. So we're using the same key for each block. We're going to get as output a ciphertext. Instead of doing each block independently, though, and having the codebook property, for the second block, we're going to take the ciphertext that came out for the first block, XOR that with the message block, and then make that the input to our encryption function. So this keeps going. This means that the result in CBC, or cipher block chaining mode, the ith encrypted block is the result of encrypting the XOR of the ith message block with the I-1th encryption block. We have a little bit of an issue with the first one. The first one, well, there's no 0th block. If we just did what was shown here, well, then we'd still have a problem that we would see repetition every time the first block in a file is the same as the first block in another file, encrypted with the same key. We get the same C0 out. So we don't want that. We're going to add what's called an initialization vector, and we'll XOR that with the first message. That keeps things consistent. Each message is being XORed with something before it's encrypted. And this might worry us that we're adding more secrets. We want to minimize the number of secrets to be as few as possible. The IV doesn't really need to be kept secret. Note that we're still encrypting this output. It's helpful to not reuse an IV though. So it's okay to make the IV something unsecret as long as it's not always the same. So the question is, suppose that Alice forgets the value that she used for the initialization vector. She encrypted some file, she has the ciphertext, and she has the key. Can she still recover M even though she forgot the IV value? So the answers are no, she can't recover any of M. Almost that she can recover all of M except for the very first block. Almost that she can recover all of M except for the first and the second block. Or that she can only recover the very last block of M. The answer is the second choice, that she can almost recover the full message, everything except for the very first block. That the point of the initialization vector is just to hide repetition among encryptions that would appear just looking at the first block. And the reason for this, we can look at how the encryption mode behaves. We saw that for all the blocks except for the first one, the value of CI is the encryption of the value MI, include my key there. And we saw for the way the encryption mode works, CI is equal to the encryption using the key K of MI XOR CI -1. The exception to that is block C0, where that's the value of encrypting M0 XORed with the IV. So we didn't explain how to do decryption, but from the way the encryption was, you should be able to figure that out. We can look at this backwards. So in order to get the last message block, well, what we need to do is decrypt using key K. And the input to decrypt is this last ciphertext block. So we're going backwards. We're decrypting. We don't have the message block yet. To get the message block, we need to do the XOR to get message block N-1. And so that means we're XORing that with the ciphertext value of the previous block, which we already have. Right? Remember, we have to decrypt, we start with all the ciphertext blocks. So this is how we decrypted the last block, but each block is the same. To get message block I, we need to decrypt ciphertext block I and XOR that with the previous ciphertext block. So we can do that for all the blocks, except for we have this exception for the last one. The encryption for the last one used this IV. To get the last message block, well, what we need to do is decrypt the last ciphertext block, or the first ciphertext block. We're going backwards now. And then XOR that result with the IV. So if we lose the IV, but don't lose the key and don't lose the ciphertext, we've lost just the first block. And if the IV was selected perfectly at random, well, we have no information at all about the first block, because whatever we get out of this decryption is XORed with that IV to get the message. So if we have no information about the IV, we have no information about the first message block, but we can decrypt all the other blocks. The next mode of operation I want to talk about is called CTR mode, which stands for counter. We have a message divided into blocks, just as before. We'll have our encryption function, just as before, and we can think of it as AES or any other block cipher. And that takes a key as input. We'll use the same key. But instead of just having a message block go in, what we're going to do instead is have a counter, some value that cycles through the natural numbers. That's going to be our input message. So we'll get out of that some ciphertext. And what we're going to do now, well, so far, none of this has anything to do with the message, right? We've just encrypted the counting values from 0 to N-1. What we're going to do is XOR those, XOR the outputs here with the message. So the message blocks go into these XORs, and what comes out is the ciphertext blocks. If we did it just like this, we wouldn't have quite as much security as we would like. We'd be vulnerable to attacks that search the space of counters. We'd also be vulnerable because we're using the same sequence of counters for every file that we encrypt with the same key. So the solution to this is similar to what we did with the initialization vectors in the previous mode. What we're going to do is add a nonce. We'll append the nonce with the counter value. And a nonce is very similar to a key. A nonce is a one-time unpredictable value. Unlike a key, it doesn't need to be kept secret. The point of the nonce is to make sure every time we use counter mode with the same key, we get different blocks out. So as an example with AES, if we have 128 bits as the block size, we might have a 64-bit nonce and a 64-bit counter. So let me summarize these two modes. So we saw cipher block chaining mode, and we saw counter mode. In CBC mode, the ith block of the ciphertext is the result of encrypting using the key. The ith block of the message with the previous ciphertext block. And we need a slightly special case for 0, which would use, instead of the -1 ciphertext block, which doesn't exist, would use an initialization vector. With counter mode, the ith ciphertext block is the result of encrypting the value of I, that's our counter, with some nonce. And I'm writing this as concatenation. So we have 64 bits here pasted next to those 64 bits for the counter and the nonce. And that is XORed with the corresponding message block. To do decryption with counter mode, well, the ith message block is the ith ciphertext block XORed with this same value, which, as we know the key, we can decrypt. So that's how decryption is done. With CBC mode, the ith message block is the result of decrypting the ith ciphertext block and XORing that with a previous ciphertext block. Or in the case of the very first block, XORing that with the IV. So now it's time for a quiz to see if you understand the differences between CBC mode and counter mode. So the question is, if Alice wants to quickly encrypt a large file, and she's got a multi-core machine, or she's got access to a large distributed computing resource, which of these two modes will allow her to encrypt the file more quickly? The choices are that it doesn't matter, that CBC mode would be faster, or that CTR mode would be faster. The answer is that counter mode would be faster. The reason for this is with CBC mode, there's a data dependency, that we can't start doing this encryption until we know the value of the previous ciphertext block. So we can't run all these encryptions in parallel. That's one major drawback of CBC mode. With counter mode, well, we can actually compute all these encryptions before we even know the message. These values and the expense of operation here is not the XORs. XORs are very cheap. Encryption is expensive. So we could actually pre-compute for a given nonce all of these encrypted counters. And then once we know the contents of the file, we can do those XORs also in parallel, but those are very quick. So all of these encrypted blocks could be computed in parallel using many processors. So that's a big advantage of counter mode over CBC mode. The last mode of operation I'm going to talk about is called cipher feedback mode, also known as CFB. There are many different modes of operation. We won't talk about them all, but the ones that I've talked about will give you a good sense of the way modes of operation work. This one's a bit different from the others that we've seen so far. It does use some encryption function as a black box, like the others. We'll call the input to that encryption the X values. So X0, X1, X2, ... are the inputs to successive encryptions. The first one will be an initialization vector, similarly to how we've used that in other modes of operation. And that will be the input to encrypt. There's also a key. The output of encrypt is some encrypted block. We'll use n as the encryption size. So for AES, we'll assume n is 128 bits, whatever the block size is. So the size of the input block and the size of the output from encrypt is 128 bits. This cipher has an additional parameter, which we'll call s. And s is how we're going to divide the output. We're going to take the first s bits of the output, and those will be XORed with the message, with that message block, producing the output ciphertext. This looks very similar to CFB, except for we haven't used the entire output here. The other thing that we're going to do is we're going to use the ciphertext to update the x value. So we're going to take these s bits, we're going to put them into the next x value, and we're going to move the old value s bits to the left. So that means we're going to be taking the n minus s bits that are the right part of the previous value of x0, and we're going to be moving those into here. Everything else proceeds the same way. We encrypt the x value, we get our output block, we take the leftmost s bits of it, we XOR those with a message, we get our ciphertext block. And this keeps going. So we can describe that process. First, we'll describe what happens with x values. So value xi is the result of taking the previous value of xi. So that's value xi minus 1, so the left value of xi. Taking from position n minus s to the end. I'm going to use Pythonic notation for this. We're taking from position s to the end of the previous value of x, and we're concatenating that with the value of the previous ciphertext. So this is defined as a recurrence. We need to define the initial value, and that was given by the IV, the initialization vector. So that's how we update the x values, how we compute the ciphertext values. We compute the ciphertext values by taking the outputs here. That's the result of encrypting using key K, the x value for that position. And we're going to take just positions up to s, and then we're going to XOR that with the message. So this is how we compute the ciphertext blocks in the cipher feedback mode. The important thing that you should notice here is there's this additional parameter s, and what s means is the size of the message block. And the value of s should be less than the value of n. That's the normal block size of the cipher. Otherwise, we wouldn't have any input left. It would end up being a different mode. So now we'll have a couple quizzes to see that you understand cipher feedback mode. So the first question is, how does one decrypt a message encrypted using cipher feedback mode? So here are the choices. The first choice is we have to go through the blocks backwards, XORing out the ciphertext from the results of encrypting the x values, and we can compute the x values in reverse order like this. The other choice is we do the decryption going forward, XORing out the ciphertext with the encrypted xi values and updating them as we did in the encryption mode. And the third choice is the same as the second choice, except instead of using the encryption function, we're using the decryption function, which is the inverse of the encryption function. The answer is the second choice. The first choice doesn't make any sense at all. The difference between the second choice and the third choice is whether we use the encryption function or decryption. And the reason that we're using encryption function, just like we did in encrypting, is because when we're decrypting, we have these ciphertexts and we're trying to get the messages. So we're just trying to go through these XORs in the reverse direction. That means we need the same exact thing that we had in encryption to XOR out, which is the result of encrypting these xi values. So for this quiz, I'm going to list some properties, and you should check the box for the ones that are true for the given operation mode. So which modes require that E, the encrypt function that we've been using in the black box, is invertible? Check this box if cipher block chaining mode requires this, and check this box if cipher feedback mode requires this. Which of them require the initialization vector to be kept secret? Can use small message blocks, which can provide strong protection against tampering. So Alice would be able to know if someone had changed values of parts of her file. And the final one, that the final ciphertext depends on all of the blocks in the message. So here are the answers. CBC does require the encryption function to be invertible, because to do decryption, we need to use the inverse of the encryption function. CFB does not, as we saw both encryption and decryption use the encryption function in the forward direction. This has advantages. That means there are more possible functions we could use for this. We haven't seen any yet, but soon we'll talk about hash functions, which could be used as the encryption function for cipher feedback mode. Neither of them require the IV to be kept secret. And one way to see this is if you look at the structure of the ciphers, they're using the IV as though it was ciphertext block -1. And all the other ciphertext blocks are visible to the attacker. So if you think about how it's used just like another ciphertext block. There's no security required in keeping the IV secret. What's important about the IV for both of these is that it's not reused, that a unique IV is used to avoid the possibility that the same block is encrypted the same way. The big advantage of cipher feedback mode over cipher block chaining mode is this ability to use small message blocks. We can select the value of S and only encrypt the message in chunks of size S. This means we can use this mode to turn a block cipher into a stream cipher, where we're encrypting messages 1 byte at a time, if we wanted to do that. It's not necessarily the best way to design a stream cipher, because we're doing a lot more work than might be necessary. This one is maybe a little unfair to ask since we didn't talk about this, but it's an important point to make is that neither of these, as we've described them, provide any strong protection against tampering. An attacker can modify the blocks, can move blocks around. The decryption may or may not look like a valid decryption, depending on what the contents are, but there's no way to easily detect that there's been tampering with either of these modes. And we'll talk about in a future class ways to provide message authentication that would make it so you can detect when tampering happens. The final property is that the final ciphertext blocks depend on all of the message blocks, and this is actually true for both. And this turns out to be a property that's very useful for what I'm going to talk about next, which is cryptographic hash functions. I'm going to motivate this with a somewhat silly example, but something that will illustrate many of the properties that are important for cryptographic protocols. As usual, we have Alice and Bob. She's Alice in case you cannot recognize her. And we have Bob. And Alice and Bob want to decide whose turn it is to charge the robo-dog. If you can't recognize my drawing, this is indeed a robo-dog. But they're not in the same place. They're trying to do this over the telephone. They would normally do this by tossing a coin. So they decide, let's try to toss a coin over the telephone. So this is the first protocol they try. So before describing the protocol, I want to define more carefully what I mean by a protocol. We've actually seen a few already, but I haven't defined what a protocol means. And a protocol involves two or more parties. And what it is, it's a precisely defined sequence of steps. And what each step can involve is some computation, as well as communication. And communication can involve sending data between the parties in the protocol. One way to think of this, it's really the same thing we mean by a procedure in computing. That's something that we can define precisely enough that we can follow it mechanically. But unlike a procedure, which is thought of normally as being followed by one processor, or at least a set of processors controlled by the same party, with a protocol, we have two or more participants involved. So that's why it involves both computation as well as communication. In this class, we're mostly concerned with cryptographic protocols, which means one more thing, that it involves secrets. And the usual reason we want to involve secrets is because we want it to be a security protocol. And a security protocol means that it provides some guarantees, even if some of the participants cheat, and that means they don't follow the steps as specified. So now let's describe our first protocol for this, and this is intended as a cryptographic security protocol. And its participants are two parties, Alice and Bob. The robo-dog that needs charging is certainly involved in this process, but is not an active participant in the protocol. And here are the steps. So the protocol starts by Alice initiating it. So she initiates the protocol by sending Bob a message that says, I'll toss the coin, you call it. Bob calls the coin, and so he sends a message back to Alice that says, I call tails. At this point, Alice tosses the coin, and she responds to Bob that, sorry, with the result of the coin toss. In this case, she'll respond, sorry, it landed on the edge. And it's Bob's turn to walk the robo-dog. So I think I won't insult your intelligence by asking a quiz about whether this protocol works well. If it was a non-security protocol and Alice and Bob trusted each other completely, maybe it would work. Bob can trust Alice to actually toss a coin and tell Bob the real result. If it's a security protocol, it doesn't work at all. If Bob doesn't trust Alice, Alice decides the result, whether Bob wins or loses. So we need something better than this if we want to deal with mutually distrusting parties. We'll call this protocol 2. And in this protocol, Alice will start by doing three things. She'll pick a value for x. There are two possible values, 0 and 1. We can think of 0 as representing heads and 1 representing tails. She'll also pick some key of length n. So this is going to be a random key. And n is a security parameter. The higher the value of n, the larger space of possible keys, the more secure the protocol will be. Let's assume we're going to use AES and we'll make n 128. And then Alice will compute a message, which is the result of encrypting using the key the value of x. And she will send to Bob the value of m. Bob receives the value of m, we'll keep track of it, and picks a guess. So Bob will generate, however he wants, a guess value that's either 0 or 1. That's like calling the coin toss. And Bob will send that guess back to Alice. Alice knows the values that she picked for x, k, and m, as well as the value Bob picked for the guess. At this point, Alice sends the key to Bob, and Bob can compute the result of decrypting with the key, the message. This is the message that Alice sent to Bob in step 1. And at this stage, Bob can check whether or not he won the coin toss, comparing the value of t with the value of his guess. If they're equal, that means Bob guessed correctly, and Alice should charge the robo-dog. If they're not equal, then it's up to Bob to charge the robo-dog. Alice needs to know the winner too, and she could do that. She can easily do that by checking if the guess is equal to x. She could also do the decryption because she has the key as well. So at the end of the protocol, both participants agree on the result of the coin toss. Now the question is this fair? So the question is, how hard is it for Alice to cheat using RoboDog Protocol 2? And by cheat here, we mean gain an advantage, be able to make the coin toss unfair in her favor. Here's the choices. There's only one correct answer. It's the easiest thing for Alice to do that would be enough to make the coin toss unfair for Bob. The answer is the fourth choice. If she can find two keys where either the encryption of 0 with key 0 is equal to the encryption of 1 with key 1, or the opposite, then at least half the time she has an advantage. So in this case, if she sends this as the message, if Bob guesses 0, she can win by revealing K1. If Bob guesses 1, she can win by revealing K0. So she's guaranteed to win. If she finds a key pair like this, well then she can do the same thing. She can reveal this as the message, and then based on Bob's guess, reveal either K1 or K0. Either of these would also allow her to cheat. If she could find a key that has this property, that for whatever key she happened to pick, encrypts 0 to the same thing that key encrypted 1 to, well, that would allow her to cheat just as well. But this is a harder thing to do than finding two keys that have this property. We might not know enough yet to be able to be sure that this is harder than that, but we know it's certainly no more difficult, and this could be easier, and we'll see that in fact it is easier. The second one would also be enough, but this is a much stronger property to find a key pair that has both of those properties. How hard this is depends on lots of things. The first thing we have to answer a little more is what encryption means here. So for the protocol, we have a value x, which is just 1 bit, and I've been writing that the message is the result of encrypting x with some key. But if we're using a block cipher, well, that assumes that the input is 128 bits. The key is also 128 bits, and AES does operate with different size keys, but the minimum key size is 128 bits. And the ciphertext out is 128 bits. So in this case, we only have 1 bit. So the question is, what should we do about this? And I'll give you 3 choices. So we could use the cipher feedback mode and set S to 1. That allows us to encrypt 1 bit at a time. We could use ECB mode. That's just using AES, passing in the input. And we could pad this input X by adding 127 random bits to the end of it. Or we could use ECB mode, padding the input with 127 0 bits added after X. For the protocol that I've described, which one of these would be the best choice? The answer is the only reasonable choice is the third one. The reason for that is either of the first two make it very easy for Alice to cheat. For the first choice, we're only looking at the first bit out of the encryption. So if she tries a few different keys, she's likely to find ones that produce outputs that differ in the first bit. Very easy to find one with this property. For the second one, it's not easy to find exactly this property. Finding this equality would be just as hard as it is with the third property. But the problem is Bob does not know the 127 bits that are added. So Bob's only looking at the first character here, and finding two keys that have this property would be very easy. So in this case, the only one that makes sense is this one. When we're thinking about encrypting files and other things, this isn't quite the right answer for padding in most cases. This solution only works when Bob knows the actual size of the input and agrees with Alice in advance to know that all padded bits should be zeros. When you don't know the size, this doesn't quite work, because if the message ends with 0 bits and we start the padding with 0 bits, we don't know where the actual end was. So the usual solution to this and there are several possible solutions, is to start the padding with a 1 bit and then all zeros to the end of the message. That means if the message actually ended here, if this was the end of a block, if the message was an even number of blocks, we need an extra block of just padding to indicate that we got to the end. In this case, since Alice and Bob both know that there's only 1 bit for the coin toss, as long as they agree in advance that the padding will be all 0 bits, that would be okay. This approach works for the coin tossing problem. But there are lots of other situations where we need to commit to values, and we need to commit to values much longer than just 1 bit. And for that, we need something a little more versatile, but with the same idea. What we need for this is what's called a cryptographic hash function. It's a function that has this property that it takes some large value as an input and outputs a small value. So this is similar to a regular hash function, like we used in the hash table. It has the property that maps values from a large input domain, and by large here, we usually mean infinite, such as all possible strings of any length, to a small fixed output size. It should also have the property that it's well distributed, that for any given input, the probability that that input maps to a particular value is close to 1 over the size of the table. And we'll use n to represent the output size. So we'll say that outputs are in the range from 0 up to n minus 1. And so if it has this well-distributed property, well, this works great for a hash table. This is not enough for cryptographic commitments. If we just had these two properties, well, it might be easy to find other x values that map to the same thing. And we saw that one of the things that we need for a cryptographic hash function is to make it hard for Alice to be able to do that. Otherwise, she could find 2 inputs and cheat in the coin tossing game. This first property of mapping a large input domain to a small fixed output we'll call compression. What we need for a cryptographic hash function is 3 additional properties. The properties are pre-image resistance, which means given the output of the hash function, it's hard to find the input that produced it. This is a form of one-wayness. The other 2 properties we need concern the collision resistance. The weakest form of this is known as weak collision resistance. What weak collision resistance means is that if we're given some hash value, it's hard to find any input that hashes to the same result. These are sort of similar, right? This one says it's hard to find the actual value of x that was used. This one says it's hard to find any x prime value that hashes to that value. If we have weak collision resistance, that would imply we have a form of pre-image resistance as well. And the final property is strong collision resistance, which is exactly the one we saw that we needed for the coin tossing game. And strong collision resistance requires that it's hard to find any pair, x and y, such that the hash of x is equal to the hash of y. So have we seen anything that can do this? And the question is, which of these is almost a good cryptographic hash function? And I'm using almost here in somewhat of a fuzzy way, but I want you to select the one that seems closest to being a good cryptographic hash function. None of them is a perfect cryptographic hash function, and we'll discuss that more after the quiz. So here are the choices. Use cipher block chaining mode to encrypt x, and then take the last output block as the value of the hash. The second choice is to use counter mode to encrypt x, and then take the last output block. The third choice is to use electronic codebook mode to encrypt x, and then take all the output blocks, XOR them all together, and use the result as the hash value. And the fourth choice is to use counter mode to encrypt x, XOR together all the output blocks, and that's the hash value. Which one of these makes the most sense to provide the cryptographic hash function properties that we need? So the answer is the first one. The property that we need is to provide this collision resistance property. All of these provide the compression needed. We're taking a large input x that could be any size, turning it into the size of 1 block. The other 3 don't provide the collision resistance we need. So with counter mode, the value of the last output block is the encryption of the last block in the message XORed with the counter value and the nonce. And that doesn't depend on any other blocks in the message. It only depends on the last block. It depends on the length, the number of blocks before that. But if we want to find that pair of values x and y that hash to the same value, well, in this case, that's easy. We can change any of the previous blocks. For the other 2, it's a little less clear to see that. The output does depend on all the input because we're XORing all those inputs into the output. But there are lots of things we could do that would still allow us to find collisions. And one example with ECB mode, well, we can just flip the messages. If we swap the first block of the message with the second block of the message, The XOR of all the output blocks will still be the same, since with ECB mode, these will encrypt to the same thing. With counter mode, the swap is not quite as simple. We'd have to adjust what's in the block to also adjust the change in the counter, but we could produce things that hash to the same value. So none of these would work. The first one is actually pretty close to what traditional hash functions used, and it's a construction known as the Merkle-Damgard construction, which is quite similar to CBC mode encryption. Since it's a hash, we don't need a secret key. We can use the same key for each step, so we could select the key being 0. There's some subtleties to make this work as a hash function, and in fact, there's a lot of controversy today about how well hash functions work. The ones that were considered the standard until recently was a hash function known as SHA-1. This was a standard accepted by NIST, and people have found ways to find collisions in SHA-1. There is an ongoing competition to select a new standard hash, to find a replacement, to find a hash function that is closer to achieving these properties. And it's expected that the winner will be announced in 2012. There are 5 finalists currently under consideration. We're not going to look any more in detail at how to construct a modern hash function. Instead, we're going to assume that we have an ideal one. We're going to assume that we have what we know as a random oracle, which is an ideal cryptographic hash function. And this random oracle assumption means that we can have an ideal cryptographic hash function that maps any input to H with a uniform distribution. And an attacker trying to find collisions can do no better than a brute force search on the size of H. So that's what we will assume we have. Before we go forward with that assumption, I want to ask a quiz whether random oracles actually exist. The answers are yes, they do, and we know of one. Maybe they exist, but we don't know of one yet. Or no, it's impossible to actually build a random oracle. The answer is no, that it's actually impossible to construct one. This function must be deterministic, so it produces the same output for the same input. We want it to produce a uniform distribution, so that means it needs to add randomness to what comes in, but that's impossible. Since it's deterministic, the only randomness that it could use is what's provided by X, so there's no way to amplify that to provide more randomness in the output. So this is actually impossible. We're going to assume they exist anyway. And the assumption is that even though it's impossible in theory to do this, that in practice we can build hash functions that provide mappings that are computationally very difficult and indistinguishable from uniform by an adversary with a reasonable amount of computational resources. So now we'll assume that we do have such a function. We'll assume that we have a function H that acts like a random oracle that provides the properties of an ideal cryptographic hash function. Let's try our coin tossing protocol again. So here's our new protocol design. Alice will pick a number 0 or 1 representing heads or tails. She'll compute using our ideal cryptographic hash function, the hash of X, and she'll send M to Bob. Bob will make a guess, send that guess back to Alice. Then Alice will send her claimed value of X back to Bob. Bob can check if the hash of X equals M. If that's not the case, then Bob suspects that Alice is cheated. And then if X is equal to G, Bob wins. So do we like this protocol? And we'll assume H is an ideal hash function. So which one of the parties, if any, or both, can cheat with this new protocol that we've defined? So the answer is that Bob can cheat. And the reason that Bob can cheat, well, remember this hash function is not encryption. There's no secrets that go into it. It's only providing this commitment to the input. And so Bob can easily cheat in this case. He can compute by himself the hash of 0, the hash of 1, check them whether they equal M, and then instead of guessing, he can pick whichever one did. So with this protocol, Bob can always win. I'm going to leave it as an open discussion problem for you to figure out how to fix this protocol. And there are definitely lots of different ways to do this. I hope there'll be some interesting discussion about it on the forums. So the next thing we're going to look at is how big does the hash output need to be to provide the properties we need. So first, let's just consider weak collision resistance. So the question is, assuming that our attacker has just enough computing power to perform 2 to the 62 hashes, how many bits should our ideal hash function, and we're assuming now that we have an ideal hash function that provides a perfect uniform distribution on the outputs to provide weak collision resistance. And to formalize what we mean by providing that, let's assume that we're satisfied as long as the attacker's success probability of finding some preimage that hashes to our value h is less than 1/2. Of course, for most applications, we want this probability to be much less than 1/2. To answer, give the number of bits in the output of h. So the answer is we need 63 bits to ensure this probability is less than 1/2. And the way to think about this is assuming the uniform distribution of our ideal hash function. Every time the probability that one guess maps to h is 1 over the number of bits, or 2 to the negative b. We'll use b to represent the number of bits. So with our random oracle model, for any given guess, the probability that it hashes to a particular value is 2 to the negative b. The probability a guess is bad is 1 minus that. And now, over a series of guesses, the probability that they're all bad is that raised to the number of guesses power. And we've said that k is equal to the number of guesses here, which we said was 2 to the 62. And we can solve 1 minus 2 to the negative 62 to the 2 to the 62. That's equal to approximately 0.63. There are lots of ways to solve this. You could try computing this in Python. These numbers get pretty big. The easiest way to solve this is to just plug this into Wolfram Alpha. There are also certainly mathematical things you could do to get this equation in a simpler form. But since we just want the answer, it's easier to just try plugging in some numbers. If we increase the number of bits by 1, that means the probability for each guess being bad increases to 1 minus 2 to the negative 63, and that turns out to be 0.39. So that means 63 is the fewest number of bits to provide the attacker with less than a 50% chance of finding a preimage that maps to the same hash value in 2 to the 62 guesses. Now, the key point is that this was for weak collision resistance. And for weak collision resistance, our assumption an attacker needs to do about 2 to the b work, where b is the number of hash bits, to have a good chance of finding a collision. Strong collision resistance is harder than weak. To obtain strong collision resistance is actually much harder, and we'll see that we need about twice as many bits for that the attacker's effort is more like 2 to the b over 2, so we'll need about twice as many output bits in our hash function to provide this. The reason for this is because of what's known as the birthday paradox. It's called a paradox. It's not really a paradox. It's a surprise to people who don't follow the mathematics on this, but there's nothing paradoxical about it. It's not like the Berry paradox that leads to a contradiction. And the way this is usually framed is you have some group of k people. Let's say it's a kindergarten classroom, and you want to know what the probability that 2 people have the same birthday. And the reason this is called a paradox is the answer is actually much higher than most people expect. So let's compute this. We'll assume that there are no leap years and that birthdays are uniformly distributed. We assume the same property for our outputs of our ideal hash function. So we'll compute the complement probability that there are no duplicates, and then the probability that there is at least one duplicate is 1 minus this. And the way to think about that is, well, we can go through the people in the class. We can assign some birthday to each one. So we'll assign B0 to the first one, B1 to the second one, keep assigning birthdays. There are lots of different ways we could do that. In order to assign birthdays with no duplicates, then there's a limited number of ways that we can pick any of 365 days for the first birthday. For the second one, if we want no duplicates, we can't use whatever day we pick for the first one. So it'll be that times 364 times 363 and so forth. And that's the number of ways to assign birthdays with no duplication. We're trying to compute the probability, so we're going to divide that by the number of ways to assign with duplication, which is just 365 choices for each person. So in general, this first value is n factorial divided by n minus k factorial. And the bottom result is just n to the k. N is the number of possible days, or the number of possible hash outputs. K is the number of trials. And so our probability that there are duplicates is just 1 minus this. This is what we need for strong collision resistance. It's higher than what we needed for weak collision resistance, which was 1 minus 1 over n to the k. So to actually compute this, these numbers would get really big if we tried to actually compute the factorials. Instead, we need to use approximations to do this. But to give you some idea what the results are like, if we have the duplicate birthday question where we have 365 days and 20 people, the probability that there's at least one duplicate exceeds 0.4. If we're thinking about hash collisions, if we only had a 64-bit hash and our attacker was much weaker than the one we hypothesized, let's say they can only do 2 to the 32, that's already almost a 40% chance of success. This success goes up quite quickly. If the attacker can do 2 to the 34 hashes, then the success probability is very close to 1. So the conclusion is that given an ideal hash function with n possible outputs, an attacker needs about n guesses to find an input that hashes to a particular value, but only needs about the square root of n guesses to find a pair that collide. This assumes the attacker can store all those hash values as they try the guesses and compare it to all the previous ones. And this is the reason why hash functions need to have large outputs. SHA-1, which was a widely used hash function, used 160 bits in its output. This is actually broken. There's a way to find collisions using SHA-1 with only 2 to the 51 operations, much fewer than the 2 to the 80 that one would expect from the square root estimate. And that's because of mathematical weaknesses in the way SHA-1 works. SHA-2, the output can be either 256 or 512 bits. As long as there aren't mathematical weaknesses in the cipher, if it was really ideal hash function, this would be big enough to defeat any realistic attacker. But they're beginning to be suggestions that there may be ways to break this. No practical breaks have been found yet. In SHA-3, the winner is expected to be announced later this year. So for the rest of this class, we're going to assume that we do have an ideal hash function and that it has enough outputs to provide strong collision resistance against a motivated attacker. So the last thing we'll do this unit is look at an application that combines many of the things we've seen so far. And our goal is to figure out how to use passwords to do authentication. We're going to assume that we have some file or database to keep track of users. And for each user, we want to keep track of something that will allow us to authenticate that user. In Unix, this file is stored in etc password. So our goal is that even if some malicious insider or someone who can compromise our system can get access to the database or the password file, they won't be able to impersonate users. They won't be able to log in by just being able to read this file. If they can modify this file, that's another story, but let's assume that they can't modify it, they can just read it. This is not a completely unrealistic model. This is actually the model that motivated the design of the Unix password system, that there are lots of people that need to read this password file, but only very privileged applications that need to write to it. So the really bad idea, number one, is to just keep the passwords in clear text. And there actually are web applications that do that. And any web application that actually does that is doing something very, very wrong. First of all, it's wrong to send a password in email, especially one that was created by a user. But it also means that they're actually storing your password in a way that they can recover it. And that probably means that anyone else who has access to their database can also recover it. So we want to do something better. We want to provide this property that even if someone can get access to the database and read all the user and password information, they can't break into your account. So that was really bad idea number 0, keeping the passwords in clear text. Now we're going to move on to really bad idea number 1, which sounds a little bit more plausible, but is not a good way to store passwords. And so here's the plan. The server operator will generate some key. Let's assume the server can generate a good random key. And for each password, we're going to store the encrypted value of that password, encrypting using the key, using CFB mode, so that's cipher feedback mode, with message block size 8. So that will allow us to use this for any size string. 8 is the number of bits per character. That could be 7 or 8, depending on how we encode the characters. The question is, why is this a really bad idea? Here are all the possible choices. Select all the ones that apply. That it reveals the length of the password. That the encrypted text reveals when two users have the same password. That it requires use of an encryption function, which is slower than using a hash function. That if the key is compromised, that reveals all of the passwords. The answer is All except for the third are true. The third is not true because encryption is generally faster than hashing. These three are really big problems with this scheme. Let's talk about the fourth one first. We need this key to decrypt. The program that's running on the server that needs to check passwords will need this key all the time. So chances are, if the password file is compromised, the key is also compromised because it's available in memory, it's stored in this program, or it's readily accessible because we need it every time we check a password. The solution to this is that we don't actually need to invert the password to check it's correct. All we need to do is recompute from the entered password some function and check that with what's stored. So there's no reason to have a key here. The first reason is also true, that because we're encrypting the password, the output that's the stored password will reveal the length. The reason that's a bad idea, well, it reveals information about the password. It also helps an attacker out, tells them which passwords are short. And that helps the attacker know which ones to try and break. The easy way to fix this is to use a hash function as well. If we use a hash function, the size of the output doesn't depend on the size of the input. So no matter how long the password is, we'll have the same number of output bits based on our hash function. The second one's a little more subtle. If we just use the hash function in a straightforward way, we won't save this problem. And this problem is pretty important. If you look at typical passwords, many are the same. And the most popular password, at least according to an analysis of leaked passwords, is 123456. If that's your password, you should probably change it. Out of the 32 million passwords that were leaked, so an analysis of the 32 million passwords that were leaked by rockyou.com, and they did not store passwords in an encrypted format, so all the actual passwords were easily revealed. The most popular password was 123456. Over 290,000 people use that for their password. That's almost 0.1%. So if this is your password, you should probably change it. Once you start looking at a set of a few thousand popular passwords, you're covering a large percentage of users. So this first approach fails on many accounts. So now we'll look at a slightly better idea. And this was actually what was done by early versions of Unix. So the idea was to store for each user the result of encrypting using the user's password as the key, the value 0. So this means there's no key to keep secret on the server. Someone who compromises the password file, well, they know that the value being encrypted is 0, but would need to test possible passwords to find the one that matches. And to make this harder, you wouldn't just run encryption once, you would run it many times. If you encrypt twice, well, this doubles the work to check a password. It also doubles the attacker's work for each password to guess. Since the attacker has to guess many more passwords than just the one that was entered, this scales the attacker's work more than it scales the checking work. And the way this worked in Unix, it was doing this 25 times. So the value that was stored for each user was the result of encrypting using the password as the key, using 0 as the initial value, but looping it around 25 times. There's some problems with the way this was done in early Unix systems. The encryption function was DES, the data encryption standard, which used 56-bit keys. And the key was generated from the password by just cutting it off. Take the first 56 bits. So with the 56-bit key, the first 56 bits of the user's password are used. If this was encoded as 7-bit ASCII, that was only 8 letters. It was actually a little bit less than that because DES placed some restrictions on the key structure. So if users selected their passwords using only the uppercase, lowercase, and digits, this corresponds to 62 possibilities. Most users would not pick uniformly from those 62 possible characters. But if they did, there's 62 to the 8 possible passwords. This is less than 2 to the 48. For someone with modern computing resources, doing a search on a space like this is very feasible. The reality is even worse than this, that a motivated attacker can pre-compute a dictionary, pre-compute this value for a set of common words W, store those pre-computed values, and then every new password file that's compromised, check all the passwords against this list, and have a good likelihood of finding some accounts that can be broken into. So how can we make dictionary attacks harder? Well, one idea would be to train users to pick better passwords. Users are pretty hard to train. This usually means coerce instead. Force users to pick a password that satisfies some properties. It could be a minimum length, a mix of upper and lowercase letters and special characters. Many websites do this. It usually just leads to annoyance and doesn't necessarily lead to better passwords. You can certainly come up with bad passwords that satisfy any set of rules that someone forces you to use. So another solution would be to protect the encrypted passwords to make sure that an attacker or an insider can't get access to them. This would certainly help, would prevent the dictionary attack because they wouldn't have access to the encrypted passwords. They could still try a small number through the login interface. If the passwords are bad enough, well, the dictionary attacker will still succeed, but only breaking a small number of accounts. The third approach is to add salt. This is the one I'll talk about next. So with a salted password scheme, what we'll store in the password file, we'll have the users, we'll have an extra column that we'll call the salt, and then we'll store the encrypted password. What the salt is random bits. They don't need to be kept secret. For the Unix scheme, there were 12 random bits. And they're different for each user. That's why they're stored in the table. So if we had, for user Ellis, let's say we have the salt 01101, which is an apparently random sequence. What we'll store as the encrypted password is the result of hashing the salt concatenated with Alice's password. And there are different ways of doing this. Some hash functions can be modified to behave differently based on another parameter. But if it's a simple hash function that just takes an input, well, we can make the input the salt concatenate with the password. And then for Bob, we'll do the same thing, but we'll have a different sequence of random bits. And so here, what we're storing is the result of hashing Bob's salt, which is this selection of random bits, concatenated with Bob's password. This means as long as the salts are different, even if the passwords are the same, the encrypted passwords will be different. And this is very similar to what standard Unix systems did, where H is actually using DES encryption 25 times, using the salt to modify how the encryption happens, and the password as the key, and the initial input as 0. So to see if you understand the impact of salting, I have 2 quizzes. So the question is, how much harder does adding salt make it for an attacker who compromises a password file, who just wants to learn Alice's password? The possible answers are not much harder at all, about twice as hard as it would be without the salt, and about 2 to the 12, which is 4,096, times harder than it would be without the salt. The answer is not much harder at all. All the attacker has to do, the attackers compromise the password file. That contains the line giving the salt for Alice and her encrypted password. To break the password, the attacker needs to try possible passwords concatenated with that salt and find one that matches the hash value. This seems like the salting doesn't help us at all, but let's change the question a little bit. So now the question is, how much harder does the addition of salt make it for an attacker who wants to carry out offline dictionary attacks? That means the attacker can pre-compute a dictionary of encrypted passwords, and then for each collected password file, wants to find any passwords that match the values found in that dictionary. Now the answer is the third one, that it makes it about 4,000 times harder. So to compute a dictionary that would be effective against all the different salts, the attacker really needs to pre-compute that dictionary for all the different salt values to be able to look for passwords that match. So salting adds a lot of value for very little cost. We just need some extra bits that don't need to be kept secret that are stored in our password file. So this helps a little bit, but doesn't avoid many of the problems with passwords. And one big problem with passwords is that they're reused. And there are lots of ways to reuse passwords. Some of this is using the same password across many sites. And that's not what I'm talking about here. I'm talking about the point that every time Alice logs in, well, she enters the same exact password. The password is the same until she does something to change it. So she's typing the same password many times. This means if there's something logging what she types, it will learn her password. If she types it in an internet cafe or somewhere where it's visible to someone looking over her shoulder, a shoulder surfer. It's also the case that her device that she enters her password in would start to have smudges where she types her password. This is particularly a problem for short pins on smartphones that are entered so many times. The finger smudges start to give an idea of what the password might be. All of these problems stem from using the same password every time she logs in. So we're going to talk about one way to avoid that, which is to use a hash chain. And hash chains have lots of interesting applications. In this case, we're going to use a hash chain to make it so we still have the nice property that we had with the password file, where the server stores no secrets. It doesn't matter if all the data on the server is compromised. That still wouldn't give someone the ability to log in as Alice. So here's the idea of how to do this. We're going to start by selecting some secret, and then we're going to compute the hash of that secret, and then we're going to do that again. We're going to compute the hash that we got for the first time as the input, and we're going to keep computing hashes here. This could be done anywhere. I've written it on the server side. The important point at the end of this, so what Alice gets is the hash of S, the hash of the hash of S, the hash of the hash of the hash of S, and so forth. Of course, if she just has S, she could compute all of these herself. The server only stores one thing. The only thing the server stores is the last value in this hash chain. So let's suppose we did this 100 times. This is the value the server would store, and that's the only value stored by the server. So now the protocol to log in will be Alice will send the 99th value in this hash chain. So what the server will do is compute the hash of P, check if it's equal to the stored value X. If it is, it will allow Alice to log in, and will also update the value of X. The new value of X will be the value Alice sent as P. So that's how the first login works. So now the question is, the next time Alice logs in, what does she need to send? Here's the choices. Different number of times of doing the hash, starting from the secret S. The answer is Alice needs to send the value of hashing S 98 times. The hash chain is going backwards. We can only verify hashes in one direction. The hash is hard to compute in one direction. That's the valuable property the hash function gives us. And so we have to go backwards if we want to use it for authentication. And here we're using it to authenticate Alice. If someone just knows X, if someone intercepts P, knows the previous password value, well, they could compute any of these other values. Those are easy to compute once you have P. Well, this was P. This one is just computing the hash of P. And this one is computing the hash of P. The only one that would be hard to compute is this one. The server can check that that's correct using the same process. At this point, the value of X is hash 99 of S. So when the value of P that's sent is hash to the 98th power of S, doing hash 98 times, well, then this equation will be true only if the value sent was correct. So what I've described is what's known as the S-key password system. And the way S-key would work, the server would generate the hash chain. Let's say there are 100 entries. Alice would print these out in a list, and they would be turned into strings that are easier to type than pure bit sequences. The server would store the last entry in that hash chain and nothing else. And so what's stored in the server could not be used to log in. The list that Alice has could be used. And I should correct this, that if Alice starts with H100 as the first thing in her list, what the server should actually store would be H101. This has a pretty big downside, that it requires Alice to carry around with her a list of passwords. And instead of remembering something that becomes easier and easier to type, well, she'd have to look at that list, type the password correctly, cross that one off, and use the next one next time. And at some point, she's going to run out. She's going to need to get on a secure connection again to generate a new hash chain to be able to keep doing this. There's an interesting story about using hash chains for hotel doors. And I'm not positive if this story is true, but I've heard it from fairly reputable sources, and it seems too good not to be true. So if you think about a hotel, you've got rooms. Let's say this is room 387. And you've got a check-in desk that may not be connected by any wire to the room. What you'd like to happen is when a new visitor checks in, let's say it's Alice, the desk at the check-in can give her a new key, and that key will allow her to open the door. There's no connection between the check-in desk and the door, and we want to know that Alice will be able to enter the room. Whoever stayed in the room previously, let's say that was Bob, shouldn't be able to enter the room anymore. At the point after Alice checks in and enters the room, Bob should no longer be able to enter it. And we like to have all this happen without needing any coordination between the desk and the door. One way to do that would be to use a hash chain. What the door will do is when it reads a card, and I'll write this in sort of Pythonish code, the door will have some stored value X. What the door will do is check if the value of hashing that key is equal to X, the stored value. If it is, the door will unlock and everything's good. We open the door with the correct key. There's another situation that we need to test for, and that's if the hash of the key is equal to x. If the hash of the key, if we're thinking about a hash chain, well, that would be the next key in the hash chain. If that's the case, we also want to unlock the door, but we want to update the value that's stored as x. We'll update that value to be the hash of the current key, hash of k. So that's our read protocol. What this means is that, well, if Bob's using the room first, his key is k1, and his key will have the value, some number of hashes on some secret, and the value of x would be m plus 1 of those hashes. And Bob keeps opening the door, going through this path through the code. There wouldn't really be a Python interpreter in the door. This could be done by something much simpler than having a full Python interpreter. Then when it comes time for Alice to open the door, well, Alice's key would have the value 1 fewer hash of s. That means that the value of the hash of Alice's key is equal to this value, hashing m plus 1 times starting from s. And that means Alice would open the door. It would change the value of x, so now it no longer works for Bob. But the next person who enters, it will work, and then it will stop working for Alice. So what the check-in desk needs to do, it needs to keep track of some secret, and it needs to keep track of the number of the guest. The initial value stored as x needs to be set. But once those are done, there's no coordination needed. Every time a new guest arrives, they'll be given a key, which is the result of hashing n times starting from s. And the value of n would be decreased by 1. So this is our design for allowing secure doors with a sequence of users. So to see that you understand it and understand hash chains well, we have a quiz. What would cause problems with this design? If a criminal could extract the stored value from the lock, if a guest checks into the hotel but never actually enters her room, or if a guest enters the room many times. The answer is the second choice. If a guest checks in but never enters the room, well, here's what goes wrong. If Alice never enters the room, then the next guest, who's very tall, who checks in, well, she'll get a key that is the next value here, which is going to be hashing m minus 2 times, but the value of the stored x is still hash of m plus 1. And that means the value of hashing this new key will only be the hash of m, which won't match the value of x. So the new guest won't be able to open the door. The hotel operator would need to do something to reset the value of n or resynchronize the door and the check-in. And apparently the hotels that adopted this way of doing keying never imagined the possibility that a guest would check in but never actually enter their room with their key. Apparently this happens more often than you might think, though. So rather than speculate on why that is, this brings us to the end of Unit 2. Our main focus for Unit 2 was how to use symmetric encryption to solve problems. For the first part, we focused on this key, the need to generate a random key, which is a very hard problem. And we saw that we could use physical randomness if we had enough available to do this, but there's no way mechanically to produce a perfectly random key. But we could use a pseudo-random number generator built using encryption to take a small amount of random data and amplify that to produce more pseudo-random data. And we saw how to use a symmetric cipher to take a small amount of random data, produce a sequence of values that appear to be pseudo-random. We also looked at the problem of how to encrypt a large file or a large message, and that brought us to look at modes of operation for using symmetric ciphers. And we talked about the cipher block chaining mode, the counter mode, and the cipher feedback mode, all of which have different advantages and disadvantages. We also looked at how to do fair coin tosses remotely, and that led us to the need for cryptographic hash functions. And we saw how to use those to check user passwords in a way that doesn't require us to keep any secrets on the server. And we also saw how to use hash chains to make it so those passwords never needed to be reused. The big problem we haven't addressed yet is how to establish a shared key. If we want to use a symmetric cipher to allow two parties to communicate, well, they have to agree upon the shared key beforehand. If you think about most ways we want to communicate today, that's very difficult. If you visit a secure website, you don't have a shared secret with them to begin with, but you want to start communicating securely with them despite not having a shared secret. And for most uses of cryptography today, this is a really big problem. We can't assume that we have a shared secret with every website that we want to use. We need some way to establish a shared secret without having one to begin with. That's the main topic of Unit 3. I hope to see you there. This question is about testing for randomness. So suppose isRandomSequence is a Python procedure that takes as input a sequence of bits that's the input S, and it outputs true if that sequence is truly random and false otherwise. So the two statements are, it's actually impossible to implement a procedure that does this. If some source produces a random sequence that are guaranteed to pass an is-random sequence procedure that behaves as described, then that source cannot be a true random number generator. Check all the true statements.
So both of these are true. In class, it was shown that it is impossible to produce a random sequence generator. But if we have is-random sequence, I'm going to sketch out how we could use that to generate random sequence generator. So the first thing that we're going to do in our generate random function is loop through all the sequences of length n. Then, for each sequence, we will run our is-random sequence test. And if that is-random sequence test returns true, we will return the sequence. We have now created a function that generates a random sequence, which, as we showed in class, is impossible. Therefore, is-random sequence is impossible. The second statement is also true. This result is a bit counterintuitive. The reason that this is a true statement is that any true random number generator must eventually produce sequences that fail is-random sequence. Presumably, is-random sequence would fail, for example, a sequence of 20 zeros, but a true random number generator would eventually produce that sequence. And this further shows the impossibility of having a is-random sequence procedure.
Now we'll have some questions about modes of operation. This question is to see if you understand the modes of operation of symmetric ciphers. Which of the modes of operation can perform most of the work to do decryption in parallel? And by most, I mean the expensive operations, which are the encryption operations, not the XOR, which is very inexpensive, that can be performed at the same time using different processors. In the lecture unit, we talked about this for encryption. Here I'm asking about it for decryption. These are the four modes to consider. Check all of the modes that can do decryption in parallel.
And the solution is that all of these modes can be decrypted in parallel. So let's look at each one of these modes one at a time. ECB can be decrypted in parallel because for each C0 that we have, we can decrypt it in reverse to end up with our original message. This can be run on one processor. We can do the same thing on this one and for all the other chunks of the message that we have. And all of those can be run in parallel. Counter mode is also decryptable in parallel. For counter mode, the important part that we need to calculate is this bit into the XOR. And we know our nonce and we know our counter in advance, so this whole chunk can be calculated on one processor. This whole chunk can be calculated on another processor, and so on. And once we calculate those, we can calculate our XORs to reverse the C1 into the message. And this can also all be done in parallel. For cipher block chaining mode, similar to counter mode, the important part, this input into the XOR again, which for the first block, we know the initialization vector, so that can be calculated. Independently, we are already given C0, which can be processed in parallel to this part. In C1, we know, and this can be processed in parallel. And again, we can calculate this, and CBC can be decrypted in parallel. Similar to cipher block chaining mode, the cipher feedback mode is decryptable in parallel. The idea is very similar to the two modes we just discussed. We need to calculate the input into the XOR. This entire chain is known in advance. From C0, we have this entire chain, which is also known in advance, and we can calculate all these inputs into the XOR in parallel and decrypt our message.
For this question, I'm going to introduce a new mode of operation, which is very similar to cipher feedback mode. So this is the way cipher feedback mode worked. The change for output feedback mode is instead of taking the ciphertext and putting that back into the X vector, we're going to take the output from the encryption and take that. So that's the only difference between cipher feedback mode and output feedback mode. So which of the following are true? Output feedback mode provides stronger protection against tampering than is possible with CFB. Unlike CFB, with OFB, it's possible to recover most of an encrypted file, even if one of the blocks in the encrypted file is lost. Like CFB, it could be the basis of a cryptographic hash function using OFB. And finally, that it would be safe to use 0 as the initialization vector for output feedback mode. Which of the following four statements are true?
Only the second one is true. Let's go through each one to see why it's true or false. OFB doesn't provide any stronger tamper protection than CFB does, and both of them don't provide very much tamper protection at all. To see this, it's quite easy for an attacker to mess with a bit of C1, and that will directly affect bits in the message. This is similar to a way an attacker could tamper with a message in a one-time pad. With output feedback mode, it is possible to recover most of an encrypted file if one cipher block is lost. We can see this because in the decrypt process, we need to calculate this input into the XOR, and that can be calculated without knowledge of C1, C2, C3, or any of the other cipher messages. Even if we're missing a cipher text block, the rest of the MIs can be XOR'd with the remaining cipher text blocks and our calculated inputs to find our message block. Likewise, this shows that output feedback mode won't make a good cryptographic hash function. A cryptographic hash function must have the property that the final output depends on all the blocks in the message. In output feedback mode, the cipher block text does not depend on previous parts of the message. For example, C2 does not depend on message 1. And this shows that we can easily change a block and calculate to the same final output. For the fourth option, no, it is not safe to use the 0 vector as the initialization vector. As with cipher feedback mode and cipher block chaining, the initialization vector is important to prevent an attacker from deriving repetition in the messages. Always using the 0 initialization vector leaves output feedback mode vulnerable to this attack.
For this question, your goal is to implement cipher block chaining. We've provided some code in the IDE to get you started on this.
Here's the function we want you to write. The inputs will be plain text, which is just an array of bits that needs to be encoded, key, which will be a bits array to be used as the key for the block encoder, the initialization vector, the block size, and a block encoder. To help understand the assignment, I've included a sample implementation of ECB mode so that you can see how plain text key, block size, and block encoder inputs work. To reinforce the idea of a black box encoder, I've written 3 examples. The first 2, non-encoder and XOR encoder, are silly toy encoders, and the last one, AES encoder, uses the PyCrypto implementation of AES. Your code should work with all 3 of these encoders. Finally, there is a test function which you can use to test your implementation. And here is my solution. First, I define an XOR function to XOR 2 bit arrays together because that's not included in the library. Next, we'll loop through the plain text array, and here we break it into block size pieces, which then gets XOR'd and then fed into the encoder. The encoder output is then saved as the XOR for the input on the next round. The encoder output is then saved as the XOR for the next loop and also added to the cipher output. And finally, the cipher is returned.
For this question, your goal is to find a hash collision. We've defined a bad hash function, which is using counter mode to encrypt and then XORing all the blocks of ciphertext that come out and using that as the hash output. And we've provided the code for a hash function. Your goal is to find 2 strings where the hash outputs are the same, but the actual strings are different.
For this problem, we have provided an implementation of counter mode to be used as a hash function. The counter mode will take in a plain text input and calculate the cipher blocks as expected, which are then XOR'd together to return the hash. Your job will be to implement find collision to find a collision given an input message. We've provided 4 test cases for you to use to see if your code works, along with some utility functions that you might find useful. Here's a diagram representing our counter mode hash function. The counter is encrypted using the key, which is then XOR'd with the message to produce the first cipher block. And this is repeated for the second cipher block, etc. Then each cipher block is XOR'd together to produce our hash value. One way of creating a collision is to swap 2 of the cipher blocks, for example, the first 2. We can write this new hash as hash prime, and it should be obvious that hash equals hash prime. So now let's look back at our diagram, and for notation, let's refer to the value coming out of the encryption as E0 and E1. Then we have M0 XOR'd with E0 equals C0, and M1 XOR'd with E1 equals C1. And we want to find M0 prime and M1 prime such that when XOR'd with E0, you get C1, and when XOR'd with E1, you get C0. We can calculate M0 prime by first calculating E0 by reversing out the XOR, and then XORing E0 with C1 to get what we want. So in the code, here is a swap blocks routine that calculates the 2 message blocks needed by first calculating the E block by reversing out the XOR, and then applying the XOR on the E block with this swapped cipher block, and then returning both of them. Here, we get the inputs used for the cipher, which we then calculate. These next lines grab the 4 blocks we need, and then we calculate the new message blocks, which then get replaced into the message, which is returned. And then to test this, we call test, and it worked. For this problem, we've calculated a sequence of numbers. There's a pattern in this sequence, and your job is to find the next entry in the sequence. As with the challenge problem in Unit 1, if you get the answer, please don't share it so that other people can have the chance to find it for themselves. Know more why about they're not realistic in practice.
So this is a good question. We use random oracles in ways to make it easier to reason about cryptography. And the definition of a random oracle is typically you've got this magic black box that you can send an input to in some range, and you get as output a random value in the output domain. And for it to be a random oracle, that value needs to be completely unpredictable. So we could think about building something like this. You could have a lookup table where for every possible input, you've produced using some good physical source of randomness the output for that input. And then you would do the lookup and get that output. And that would behave like a random oracle, that those inputs would be totally random. There's no correlation. The problem is if we try to make that function any smaller. So instead of having a table where for every input we can look up the corresponding output, we want something smaller. And that's what we want with a hash function. That's what we want for any practical use of a mapping between inputs and outputs. And we can't have a full table. That would be just a huge amount of memory. And the random oracle, it turns out to be a useful device for reasoning about cryptography, where we assume that this black box exists and has this perfect ideal behavior. It's not something we can actually build. And we have to be really careful when we reason about cryptography using this assumption about a random oracle, and then we say throw in a hash function that we think behaves sort of like one, because no hash function actually behaves like a random oracle.
For our next question, Saeed Bashir wonders, by looking at a ciphertext, is it possible to figure out the encryption scheme that is used?
So for most academic work in cryptography, people assume they know everything about the scheme being used and are trying to find some mathematical weakness that allows you to solve it quicker than you could by doing a brute force search on the key space. For a lot of real world cryptography, that's not the case. The first thing you've got to do is figure out the scheme being used. That's sort of like the challenge question from homework 2, where if I told you the scheme for the random number generation, it would be easy to figure out the next one. And that's more of a better model for most cryptographic work that academics do, is assuming you know the scheme, trying to find mathematical weaknesses in it. For a lot of practical cryptography, certainly going back further, but even today, it's not the case that you know the scheme. And if the scheme is good, then even if you know it's one of a set of known schemes, you shouldn't be able to tell from the ciphertext. The ciphertext should be purely random, should look like purely random values. So unless there's some weaknesses in the encryption scheme used, you shouldn't be able to tell what it is. But there are weaknesses in all encryption schemes used. And this is particularly an issue if someone invents their own encryption scheme. They think, oh, it's going to be super secure since I've invented this custom scheme just for my own use. Those schemes almost always have weaknesses in them that even if the scheme's not known, make it much easier than breaking a known scheme where the key is not known. So it should be the case that you can't tell anything about the scheme from the ciphertext. In practice, that's probably not the case unless the scheme is a good one.
Yeah, I guess this kind of goes back to the importance of keeping your keys secure.
Yeah, so this is going back to Kirchhoff's principle, is you should be able to have a cipher that even if the adversary knows everything about the scheme you're using, as long as they don't know your key, you have a good argument why that's secure.
Okay. And then I guess the last question comes from Pavel. He has a question about invertibility. It's not obvious why encrypting different messages with a fixed key cannot give you the same ciphertext. Is this necessary for correctness?
Okay, so the question, if you have two messages that encrypt to the same ciphertext, when you try to decrypt them, well, you can't know which one to get, right? So this is why, in order for a cipher to be invertible, we need to have the property that each ciphertext corresponds to exactly one input. Mm-hmm. There are probabilistic ciphers, so there could be more than one ciphertext that corresponds to the same input under the same key, but it can't be the case that the same input under the same key, or it can't be the case that there are multiple inputs with the same key that map to the same ciphertext, because then when you try to decrypt it, even though you've got the key, you don't know which one of those two messages was the input. So we need this property that each ciphertext can be decrypted to exactly one message, otherwise decryption doesn't work.